Welcome to this explainer on sensor technology. Today, we're skipping past the dry theory and jumping straight into the gritty, real-world engineering applications that literally make modern infrastructure tick. Let's look at exactly how the physical world gets translated into the digital one.
Here is our roadmap for the day. First, what is a sensor? 2. Classifying the sensor universe. 3. The rules for selecting a sensor. Then we're doing 2 deep dives, proximity sensors for number 4 and flow sensors to wrap it up at number 5.
All right, let's jump right into section 1. What is a sensor?
Now just look at the sheer scale and variety of what's out there today. I mean, from gas sensors and gyroscopes to soil moisture detectors, it's a sprawling, kind of chaotic universe of hardware. And honestly, this proves exactly why engineers need a strict framework to classify them all, because without that solid framework, it's just a pile of circuit boards and wiring.
So, at its absolute core, a sensor is the fundamental bridge between physical phenomena and our electrical systems. Whether it's detecting light, heat, motion, or moisture, it is the required building block for literally everything, from your everyday consumer electronics to massive industrial manufacturing plants, right down to life-saving healthcare devices.
To ground this abstract definition in reality, let's look at a beautifully simple example, the light-dependent resistor, or LDR. The physical input here is just light. When light hits the LDR, it directly changes its electrical properties. Specifically, as the light gets brighter, the electrical resistance of the device actually drops. It's this elegant, immediate translation from a physical state in the real world directly into an electrical reality.
Okay, moving right along to section 2, classifying the sensor universe.
First up, we classify by the conversion process itself. We contrast direct sensors with indirect sensors. Now, a direct sensor converts a non-electrical stimulus straight into an electrical signal without any messy middle steps, kind of like how a thermocouple seamlessly turns temperature right into voltage. But an indirect sensor requires multiple conversion steps. A fiber optic displacement sensor, for instance, might have to transform light to photons and then photons to current just to get the job done.
Next, we separate them by their power requirements. We've got active sensors, sometimes called parametric sensors. Now these need an external power source, some external juice to actually operate. Think of strain gauges or carbon microphones. On the flip side, we have passive sensors. And these are self-generating wonders. They literally create their own electric signal from the stimulus itself, no external battery required. Thermocouples and photodiodes fall right into this highly efficient category.
This next category brilliantly illustrates the difference in physical interaction. Basically, does the tool need to physically touch the stimulus? A contact sensor, like your traditional strain gauge, absolutely requires physical contact to read the data. But a non-contact sensor, it can read data from afar, completely untouched, using magnetic or optical fields. It's exactly like when you use an infrared thermometer to check a surface temperature from all the way across the room. Finally, we look at the baseline of the data itself. Is the reading absolute or is it relative? An absolute sensor reacts on a fixed absolute scale. So a thermistor, for example, is always going to read the absolute temperature. A relative sensor, however, measures a stimulus relative to a fixed or variable reference point. So when we measure pressure, it's very often relative to the current atmospheric pressure, which, as you know, changes.
Which brings us to section 3, rules for selecting a sensor.
Let's ask the practical, boots-on-the-ground questions an engineer actually faces in the field. First, what is the absolute minimum and maximum range your project requires? And crucially, what's your acceptable margin of error? Because let's face it, every sensor in the world has a margin of error. The real question is simply whether your specific application allows you to tolerate it.
So the trick is balancing these core performance metrics. We all want high resolution, that smallest detectable change, but there's a catch. If your resolution is too high, it might pick up minute, unwanted fluctuations or background noise that's going to require complex additional processing to filter out. We also want high sensitivity, which is the output change per input change. But higher sensitivity almost always means higher cost. And remember, never confuse accuracy with precision. Accuracy is how close you are to the true value, whereas precision is your ability to reproduce that exact value over and over again under the exact same conditions.
But beyond the pure data, you also have to consider the brutal realities of the physical world. Your sensor might look perfect on paper, but can it survive the actual environment? Extreme temperatures or a little too much humidity can ruin a perfect sensor. You also need to minimize response time lag. Make sure you have a strong signal-to-noise ratio and figure out your calibration frequency. Plus, does it interface seamlessly with your existing instruments, or is it going to introduce new power source errors? Can it adapt via over-the-air or OTA updates? These physical and system constraints dictate your final choice just as much as the raw data specs do.
All right, let's get into Section 4, Deep Dive on Proximity Sensors.
Here is the ultimate showdown in proximity sensing. On one side, we have inductive proximity sensors. These operate on the principle of electromagnetic induction. So when a metallic object approaches, it induces eddy currents, which instantly changes the sensor's output. They only detect metal, but man, they are incredibly robust. On the other side, we have capacitive proximity sensors. These use an electrical field between two dielectric plates. When an object enters that field, it alters the capacitance. The real magic here is that capacitive sensors can detect almost anything, both conductive and non-conductive materials.
To put this into perspective in the real world, you're going to find inductive sensors serving as the absolute backbone of heavy industry. Because they are so incredibly reliable at detecting metal, they run automated manufacturing lines, manage collision detection, and handle speed sensing. Capacitive sensors, on the other hand, are the versatile heroes of tricky materials. Since they can detect nonmetals, they're heavily used for level sensing and liquid detection, especially in harsh environments. In fact, you'll constantly find them inside automatic pump control systems, diligently detecting water levels.
And that leads us to Section 5, Deep Dive on Flow Sensors.
By definition, flow sensors measure the exact rate of movement of liquids or gases safely contained within piping systems. It's a completely non-negotiable metric for maintaining pressure and chemical safety in any large-scale operation.
Now, among the different types of flow sensors out there, ultrasonic flow meters really stand out. They are non-intrusive volumetric flow meters that use acoustic vibrations, specifically Doppler and transit time technologies, to measure the flow rate. What makes them so highly prized is that because they don't block the pipe at all, they cause a very low pressure drop, require incredibly low maintenance, and offer fantastic chemical compatibility since the sensor itself never degrades in the fluid.
But here is the fascinating gotcha detail with this tech. Because ultrasonic meters rely on acoustic vibrations bouncing off particles, the liquid actually needs to be conductive or at least somewhat dirty to reflect the acoustic waves back to the sensor. Because of that, these highly advanced, incredibly sophisticated meters are completely useless if you try to measure pure, clean drinking water or distilled water. The waves literally just pass right through without reflecting. It's a perfect example of why understanding the physical environment is just as critical as understanding the electronics.
And that brings us full circle. We've moved from the basic definition of an electronic sensor, acting as a bridge to reality, all the way to the quirky reasons why perfectly clean water completely defeats advanced acoustic flow meters. Every single sensor solves a highly specific problem, but introduces its own unique limitations. So, as these technologies continue to get smaller, cheaper, and way more precise, giving us an ever-expanding universe of tools, it makes you wonder, what unseen, invisible data points in your own physical world will we unlock next? Thanks for tuning in to this explainer, and keep questioning the unseen world around you.